So the other day, I looked at using the IntersectionObserver API as a means to defer template bindings in an Angular 11 application. And just to recap, what I mean by that is that if we look at these individual items here, we can see that there is this span that interpolates a value. And if we scroll down to the very bottom of this, let's get all the nodes here, what we can see is that within the last li element, there's actually no span. And that's because this li element is not in the browser viewport, which means that we're actually deferring the interpolation, the template bindings there. In fact, if we scroll down to the bottom, what we will see is that this span shows up because this parent element is now in the viewport, which means that we're allowing that interpolation to take place. And if we scroll back to the top, we can see that this span disappears, again, because this li element is not in view. Now, when I first looked at this, the approach that I was taking was that each one of these li elements received its own intersection observer, which meant that we have in a list of 1,000 elements, 1,000 instances of the intersection observer. And that made me consider the performance. And is there a performance difference between having 1,000 intersection observer instances versus one shared instance that each li element would then consume? And what I've done here is set up two different demos. Demo A, which uses the one instance per element approach, and Demo B, which uses the one instance per list approach. And there's a single list here, so we only have one instance of the intersection observer. And before we dive a little deeper, let's just look at the HTML to see what's going on. So if we look at Demo A, which uses the single instance per element, what we can see is that we have this bn intersection observer A directive, and that is going to be bound per li element. And if we have 1,000 elements here, that means, again, we have 1,000 instances of this intersection observer. The intersection observer is then exposing itself as this intersection value, which I'm then piping, so to speak, into the ng switch, which then allows us to defer the interpolation of the string based on the visibility of this element. Now, let's contrast that with the second demo, Demo B, in which case we have two different directives working in tandem. We have on the ul element, this bn intersection observer B list directive. That's what's going to create the instance of the intersection observer. And then we have a bn intersection observer B directive, which actually injects the list directive into itself in order to set up the observation. It then works the same way as the first demo. It exposes this intersection class, which then exposes an isIntersecting property, which allows us to defer the template binding based on the ng switch. So the low-level mechanics are exactly the same. We're exposing an isIntersecting property, which is allowing us to use the ng switch bindings to defer template interpolation. The main difference here is that in the second demo, we only have a single instance of the observer, intersection observer, which we're then consuming at the lower level. And we'll look into the actual TypeScript code behind for this, but first let's just jump back and look at the performance. So immediately what we can see is that when we jump back and forth between the lists, there is a very obvious performance difference, right? When I go to list B, there's a very, very quick flash of unbound content. And then if I go back to list A, you can see it's a much slower flash of unbound content. And in fact, if we open up the elements, it gets, we can see another, just elements, because of Chrome, it slows down the performance even more. If we jump to the bottom of this list, we can see there's definitely some jank as we're scrolling, and we see a lot of unbound or uninterpolated template content. And if we switch over to the second list and we scroll down, we can see almost no jank at all, right? It's hard to differentiate the jank from the actual scroll speed itself. So we can see that that shared instance is, in this case, much faster. Now, and if we look at the performance, we can actually see this even more clearly. So let's garbage collect, and let's turn this on. And now if we jump over to list A, and then go B, and A, and then B. Let's go back to A one more time. And now let's look at the performance. let's give it a second to compile everything. What we can see is more colored magnitude of performance difference. So here, if we scroll in tight to this is switching over to task A, or to demo A rather, what we can see is that this takes a little over a quarter of a second to run all of those intersection observer callbacks. And if we switch over, if we scroll in on, zoom in on the second one here, what we can see is that in this particular case, it's a little bit hard to tell, but I think this is the intersection observer callbacks. It's under 16 milliseconds. So this is actually faster, I think, than the frame rate of the browser. So huge difference. I mean, they're both really fast, let's be honest, right? A quarter of a second is really fast. But the shared intersection observer instance is like an order of magnitude faster, close to an order of magnitude faster. And now it might seem from this that it is very clear that the intersection observer is going to be faster when it's shared. But if we start to dig down deeper into what's actually going on, it becomes a little less clear. But before we do that, now let's jump over into the Typescript to see how these two things are working under the hood. So in demo A, which has a single directive on the LI element, which means that we have 1,000 instances of this directive in this demo, if we jump into what this directive is doing, what we can see is that in the ng on init, we're instantiating an intersection observer, we're passing it a handler, and then that handler is just exposing the is intersecting of this particular host element. And because we know that we have an instance of the intersection observer per LI, we can safely assume that we're only dealing with a single entry here, which is why we're just going to grab the first one. Now let's contrast this with the demo B, which has two directives working in tandem to create the same effect. And if we look at the code behind for these, and I've put the two directives in the same Typescript code behind, here is the list directive, and we can see that the list directive instantiates an intersection observer for the list. So this is going to be the shared instance of the intersection observer. And what's going to happen is that if we look at the second directive here, this is the one that's on the LI elements, or the list item elements, what we can see is that it's injecting that parent directive. So it's taking this directive and it's injecting it into the LI. And then in the ng on init, instead of instantiating its own intersection observer, what we do is we reach up into the parent directive and we say, observe my native element, and when the intersection property of that element changes, invoke this callback. And if we jump back up here to our list directive, what we can see is that whenever the callback for the intersection observer changes, we loop over the entries, we look for the callback mapping for this target, and then we invoke that with the is intersecting property. And what we can see is that when you add an element to the parent directive, we set up this mapping between the native element and the callback. And we're going to use the ES6 map construct there in order to maintain that association. So I just wanted to be very clear here that the amount of work that's happening from the intersection observer standpoint is roughly the same. If we look at the demo A, right, we have 1,000 instances of this directive. We have 1,000 instances of the intersection observer, which has 1,000 handlers, right? Because we have 1,000 of these and each one of them gets their own handler. So let's say roughly there's 1,000 directives and 1,000 callbacks happening. Demo B is actually pretty much the same. We only have one instance of the intersection observer, but we do have 1,000 instances of these directives, and each one of these directives is passing in a callback. So we have 1,000 callbacks. So in both examples, we have 1,000 callbacks being invoked when the intersection observer changes or observes changes in the DOM. The difference is that we only have a single shared instance of the intersection observer in the second demo. Okay, now that we understand the mechanics of how everything's fitting together, let's look at what happens in the flame graph. So let's go back to our first demo here, which is demo A, the intersection observer per LI. And if we start to dig down into all this work that's happening, we can see lots of little individual things. And if we scroll down, or we zoom in deeper and deeper and deeper, and we look at these individual little work bits, what we can see here is a function call, and this is probably our function. And we can see the zone, the ng zone, the angular zone being interacted with, and we see a bunch of stuff here. And then at some point, we see this, detect changes. And so what we can see is that when the intersection observer callback is being invoked, the angular zone is seeing that change and then triggering a change detection digest after our callback fires. And if we, again, zoom out, what we can see now a little bit more clearly is that all of these change detections are happening. So we have 1,000 instances of the intersection observer API, each of which has a callback. So we have 1,000 callbacks. And after every one of those callbacks is invoked, we get a change detection being triggered in Angular. And if we, again, jump over to the faster version and we look at its flame graph now, what we can see is that we have that same sort of thing happening. We have our zone interaction, our run guarded here, and some change detection happening. And then we get back here, and here we only have a single change detection digest being triggered. And again, if we zoom out, right, we can see that there's only a single change detection happening. And that's because we only have a single intersection observer with a handler being bound. So when that handler gets invoked, a single change detection digest is triggered. Again, contrasting that with this, in which we have 1,000 change detections being triggered, one per intersection observer handler. So when we first look at this demo, it seems like the performance bottleneck is the fact that we have 1,000 intersection observer instances versus the one instance in this version. But when we dig down deeper into the flame graph, what we can see is that the actual bottleneck may be the fact that there is so much change detection happening when we have 1,000 intersection observer handlers being bound inside of the Angular zone, which begs the question, what happens if we bind the intersection observer outside of the Angular zone and then mark these li elements for check when when an intersection change happens? Well, I don't know that answer yet, but I'm going to definitely be looking into that comparison in a future blog post. So at first blush, again, it seems like having a single demo or a single shared instance of the intersection observer is much faster. But as we dig deeper into what's actually happening under the hood, the takeaway from this experiment becomes a little muddy, a little fuzzier, a little less clear. Clearly having a shared instance of the intersection observer leads to a faster outcome, but the route by which that is happening is still maybe a little bit fuzzy and worthy of some future investigation.